And let me know in the chat that you can see my screen okay. You should see the slide automated program analysis using machine learning. Does that look good?
Looks great.
Excellent. All right. Once again, I'm Hahna Latonick, and in attending this workshop today, I want you to have the confidence to find data patterns using unsupervised machine learning. You're going to learn how to develop supervised machine learning models for classifications and predictions. And we're also going to evaluate and measure the effectiveness of our ML systems, right? So we want to make sure that what we're creating is accurate, it makes sense, and that the results are useful and meaningful. And so throughout this workshop, you're going to get the hands-on experience, knowledge, and confidence to conduct automated program analysis using machine learning. And again, this workshop is going to be a very small subset of my class that's being offered in February. So looking forward to that. So these are the main topics that we're going to cover. I'm going to provide a primer to machine learning. We're going to discuss unsupervised machine learning algorithms, how to evaluate ML performance, and then we'll touch upon supervised machine learning. So for our schedule, it's 11 o'clock Eastern here in sunny Florida. So we're going to cover pretty much the first hour with lecture as well as demonstration and lab. We'll take a break at 11:50, 10-minute break, and then at the top of the hour, we'll rinse and repeat with another set of lectures, demonstrations, and labs, and then we'll wrap up on this beautiful Saturday. So why exactly should you be listening to me? Who am I to begin with? So let me just set the stage here, and then we'll quickly get off this slide. For the past 15 years, been specializing as a security researcher throughout the defense industry. I've been featured on a variety of different news outlets as a cybersecurity subject matter expert. I've trained and developed security researchers at one of the top 5 aerospace and defense industry companies. I often teach at offensive security training classes, such as at Ring Zero and B-Sides Orlando. I currently serve as the Vice President of Research and Development at a cybersecurity firm. And in the past, I've led 3 tech startups related to computer security, serving as CTO of 2 of them, as well as Director of R&D. One of my most proudest achievements is serving as a DEF CON CTF finalist back in 2014. It was an intense, surreal experience. We'll never forget it. And for that competition, our team came in 6th place, ranking the top 1.5% of ethical hackers worldwide. If you've ever taken the Offensive Computer Security 2.0 class that's offered online for free, I've served as a co-instructor for that, teaching the reverse engineering topics. Also hold a CISSP and CEH certifications, and lastly, hold a BS and MS in computer engineering, along with a mathematics minor. But we all know that in the cybersecurity field, a college degree is really just a piece of paper. It's all about your hands-on experience, which is what we're going to offer you here in this workshop. So if you're looking for a security research internship, full-time job, or new position, feel free to reach out to me with what you're looking for, what you're interested in. I'm always looking for new candidates and great people to work with. If you want to be notified of future offensive cybersecurity trainings, you can email me at that address as well. And of course, follow me on Twitter. That's my handle. And don't forget to also follow Ring Zero to keep up to date with our conference activities. So with that, let's dive right into machine learning. So what exactly is machine learning, right? It's been quite the buzzword for several years, probably over a decade now. But what exactly is machine learning? Well, essentially, it involves algorithms that are learning from data in order to solve problems that are usually too complex to solve with conventional programming. And then you might hear that and say, well, what exactly does that mean? So with conventional programming, Typically, you're going to create a program, and that program is going to accept input data. And then based on the programming logic, it's going to then generate an output, right? Whereas machine learning is quite the opposite. Typically, with machine learning models, they're going to accept input and output data if that output data exists. That's going to be fed into the algorithm, and that algorithm is going to discover relationships and essentially the rules of the problem with the goal of training the machine to solve the problem on its own. So let's look at an example to illustrate this, right? So say you have a conventional program where you provide input data, say x equals 1 or x equals 2. And you've developed the program to take that input, multiply it by 3, and then return the answer, right? So your program would output y equals 3 or y equals 6. But from the machine learning perspective, what this experience entails is that you're going to provide it with the input data of x equals 1 and x equals 2, along with the corresponding output data of y equals 3 and y equals 6. So the machine learning algorithm is going to study the relationship between the input and output data and realize, aha, the relationship is that it's going to predict the rule, hey, if I multiply my input by 3, I'm going to get the corresponding output, right? So if you were to then provide a new input, say x equals 3, then the machine learning algorithm is going to predict that the answer is that y equals 9. So why would we want to use machine learning? Well, it's become a very critical tool for deriving intelligence from data and converting that information into knowledge, especially actionable knowledge. Machine learning techniques, they're used to automatically find valuable underlying patterns within complex data that we would otherwise struggle to discover on our own as humans. As well as it'll find patterns that we probably never even would have thought of, right? Which is pretty exciting with machine learning. And so these hidden patterns and knowledge about a problem can then be used or leveraged to predict future events, as well as perform all kinds of complex decision-making more rapidly and accurately than humans. So I'm going to pause here real quick. I just wanted to let everyone, if you weren't aware in the Zoom reminder emails, there's a link in there that provides access to the workshop materials. So if you're wondering how you can get access to these slides or to download the virtual machine that we'll use in this workshop for our demonstrations and lab exercises, make sure to grab that link. And in case you don't have it, we'll have Cherry share that in the Zoom chat link as well. All right, we do have a quick question. Cherry, if you could address that in the chat, that'd be great. Thank you. All right, so applications of machine learning. Our everyday lives are impacted by machine learning, whether or not we even realize it. But here are some of the common applications in which machine learning is applied with respect to cybersecurity. It's often used for malware detection and classification, as well as detection of threats, especially like network threats. It's utilized for network device or IoT device detection. Oftentimes, systems or applications will utilize cryptographic algorithms, even if they're proprietary. So machine learning can help classify the type of cryptographic algorithms that have been implemented. It can be helpful for recovering toolchain provenance. So for example, if you're analyzing a binary and you have no idea what compiler was used or compiler settings, and perhaps Ghidra or IDA Pro is unable to detect it as well. There's an opportunity to apply machine learning to that problem. Very similarly, applying machine learning for binary decompilation. Oftentimes, machine learning can be utilized to help determine the original authors of, I would say, a product or software, and it's often useful with regards to binary code clone detection, right? So this can be helpful if you're looking at, hey, did person B or company B rip off or try to make a copy of another company's software. It's also very useful for function recognition. Again, if you're analyzing an exotic binary that IDA Pro or Ghidra has trouble analyzing, this is where ML can come into play. In an area that continues to get increasing detection or attention, I should say, is using ML for vulnerability discovery. And if there's an opportunity to make a log4j joke, here it is right here. All right, so with that, we're going to continue to pull the layers back on machine learning. So there's 4 well-known, well-used classes of machine learning. You have unsupervised, supervised, reinforcement, and deep learning. In this workshop, we're going to touch upon unsupervised as well as supervised. But for your awareness, there are these other 2 classes of machine learning. And in my class that's offered in February, we actually will explore deep learning in addition to unsupervised and supervised learning. Hopefully, maybe in August, for the August offering, I might include reinforcement learning as well. So definitely keep an eye out for that. So what exactly is unsupervised learning? So this model works on its own without supervision or guidance, as it tries to explore and discover patterns and information that was previously undetected. Only the input data is provided. It doesn't receive any answers or output to learn from. It's just given a data set and it's like, go, like, good luck, figure it out. The data is typically unlabeled. And so there's 2 main unsupervised learning techniques that are utilized, called clustering, which allows you to group your data into clusters based on their relationships of their features, as well as associations, right? For example, given how this, given the features of this binary, it's quite associated with another binary. And so there's common algorithms that are used for unsupervised machine learning, including k-means and hierarchical clustering. In this workshop, we'll touch upon k-means, and in my class in February, we do a deeper dive with hierarchical clustering. So why would you want to use unsupervised learning, and when would be a good time to apply it compared to supervised learning? So it's great for unlabeled and uncategorized data sets. It's very common to either collect, generate, or receive data that has not been labeled, that has not been categorized, and it's really up to you to do that. So that's what makes unsupervised machine learning a great starting point to better understand what your data consists of, so that once you have information to start labeling and categorizing, that then prepares you to do another layer of analysis using supervised machine learning. It's very useful for exploratory data analysis and knowledge discovery, as well as finding features which can be valuable for categorization. Another great reason to use it is that you do not always have input data with corresponding output data. And so if that output data doesn't exist or is very minimal, don't worry, all is not lost. You can still use unsupervised learning. There's a couple benefits. Oh, there's a lot of benefits, but here's a couple that I wanted to highlight as far as advantages for unsupervised learning is that, again, it's easier to get unlabeled data in comparison to labeled data for analysis. And there's no previous knowledge necessary, right? You're just given a data set, and then you apply unsupervised machine learning to start exploring that data a bit more intelligently. And through that process, you start gaining the necessary knowledge and insights about the data that you have. However, it's not perfect. There are some downsides to it where, intrinsically it's more difficult without known output. Especially it's like you're exploring your data. Am I headed in the right direction? Is this complete? Does this make sense? And because of the amount of time and resources it takes to perform that exploration, it can be more computationally complex. There's also no feedback, right? Because you don't have the corresponding output or the answers, right? You don't have that cheat sheet. You essentially have to take faith in your results, in your data, and analyzing it enough to build your confidence that, yes, these results are correct. And as a result of that lack of feedback, there is a decrease in the accuracy of the results. Because again, you're making your best educated guess and analysis of the data that you have. So here are some applications for unsupervised machine learning. It's very helpful in creating clustered data, where you're clustering your data into smaller groups based on their attributes. It's useful to recommend or find related items. So like, for example, if you're binge watching Netflix and Netflix is like, hey, we recommend this new thing to watch, or you're on Amazon, because we all buy from Amazon, especially for the holidays. Amazon might recommend something else for you to buy because you bought this other item. So that's unsupervised machine learning at play as well. It's very useful for anomaly detection, whether looking at network traffic anomalies or malware and binary anomalies. And it's also very helpful for feature reduction. So it's very easy to get overwhelmed by the amount of features that you might have to analyze. And so with unsupervised machine learning, it allows you to hone in on like what really matters and what's really significant in your entire data set, so that you can just reduce it down to those key features and really do your analysis on that, I'd say, more significant subset of data. It kind of helps cut through the noise at the end of the day. All right, so we just covered unsupervised machine learning. And I'll move this down just a bit. There we go. So how does unsupervised machine learning differ from supervised? Well, this model will learn the relationships or rules to map inputs to your outputs. It trains on known input-output pairing data, which is very helpful in predicting outputs for new inputs that it hasn't seen before, right? So similar to what I had mentioned earlier, if you have input of x equals 1, x equals 2, output y equals 3, y equals 6, right? That input-output pair data helps to inform or train the machine learning model of what that relationship is. So if it sees new input, it can easily predict a new output. The data is usually labeled, which is very helpful. And the two main techniques for applying supervised learning includes classification, where you're making a prediction, right? For example, is this malware? Is it benign? As well as for regression, where maybe you're trying to predict the next stock price or the next price of like Bitcoin, or anything that has like a numerical value that you're trying to predict, a continuous value. So common algorithms that are used for supervised learning includes decision trees, which we'll cover in this workshop. We have an exercise and demonstration for that. Also random forests, which builds upon decision trees, as well as logistic regression. And so those final two algorithms we actually cover in our February class. So we'll whet your appetite with decision trees. And if you just love supervised machine learning, highly recommend checking out our class in February and exploring additional resources online as well. So supervised learning is very useful for predicting number-based problems, as well as category-based problems, as I mentioned on the previous slide. And I'd say the main benefit and advantage of supervised learning is that you have this ground truth, right? You have the corresponding output to your input, right? So given that you have that cheat sheet and the answers, it's very useful. There's the opportunity to get feedback, right? So given this input in my prediction, was I right? If I was wrong, what was that deviation like? So that you can then go back and fine tune your model. So essentially with supervised learning, you're making predictions made based on prior knowledge. It's also highly accurate. And again, because you have that ground truth data and that feedback. Also, because supervised learning doesn't necessarily have to do all that heavy lifting, it has lower computational complexity compared to unsupervised learning. There are some disadvantages to this approach, right? It's very easy to introduce bias into its learning and decision making. And this is very important and something that I emphasize in all my classes related to this, is that you have to be very mindful of the potential bias that exists in your model. Whenever someone says, oh, our model isn't biased, I don't believe you. And so what this means, like essentially your machine learning model is making decisions based on its input, right? If it doesn't have enough data, then it's not going to be as accurate. If your data is unbalanced, then it's going to potentially predict or classify things one way, just again, based on its data, when in reality, it should be classified differently, right? So whenever you're doing machine learning, always keep in mind potentially how are my results and how is my model potentially biased. Training is time and data intensive, because again, it's being mindful of, it's analyzing those relationships between the inputs and output, and gathering a lot of reliable labeled data is difficult, right? So again, usually it's common to take an unsupervised approach, be able to categorize and label your data appropriately, which will make the supervised learning phase a lot easier, right? So again, if you do have labeled data, first thing you should think of is, okay, let me try supervised learning first. So supervised ML models, there are several applications with regards to cybersecurity, very useful and accurate for malware classification, as well as threat detection. Very useful for spam filtering. I definitely appreciate that because I'm tired of still to this day getting spam. But you know, it's definitely improved over the years, as well as vulnerability discovery. So I know we're going to go through a lot in this workshop, but here is a key slide for you to make note of and for you to walk away with, right? So regardless of the problem that you're going to attempt to analyze and solve using machine learning, here's the methodology that I recommend, that I personally use, so that you're going through the proper stages in the proper sequence to ensure that you get the end result that you're looking for. So first, you're going to collect your data. Either someone's going to give you a already prepared data set, or you're going to download one, or sometimes you just have to generate that raw data yourself. But once you have your data, you're going to perform data pre-processing. And what this involves is cleaning your data so that you don't have any missing information. You want to make sure your data set is complete and that the values in your data set are correct for further analysis, right? So once you have a clean and complete data set, you're going to then move to the next stage of selecting and extracting your features. Essentially, the features are what describe your sample, right? And so you can have a lot of features. You can start with a subset, but you at least want to pick a handful of features that you want to provide as input to your machine learning model. And then the next step is creating your vector space model. This is a fancy way of describing your data set as a list of features. And with those lists of features, you can translate them to numerical values that will allow you to plot your data. And then you're going to, so now that it's in this vector form, you're going to apply your machine learning algorithm, whether it's unsupervised, supervised, et cetera. Once your model performs its analysis and returns its results, you're then going to evaluate the performance of your ML model, right? You want to know how well it performs, how accurate is it. There's a variety of metrics that we use to assess the performance of our model. And we want to have great confidence that this model can best reflect, analyze, and essentially model our data, right? So again, this is the machine learning pipeline process. If there's nothing that you take away from this class, at least make sure you walk away with this methodology. All right, so to recap, right, there's 4 different types of machine learning classes. We're going to touch upon, we touched upon unsupervised and supervised learning. And again, for your awareness, reinforcement and deep learning are also used, but we do cover that in our February class, going deeper, no pun intended, into deep learning and perhaps reinforcement learning in August. All right. With that, we can take about a minute or two for any questions that the attendees may have before we dive into our lab. So Cherry, you can just let me know if anyone has written anything in the Q&A, or actually I will stop sharing here, see if there's anything in the Q&A. Nothing there, and doesn't look like there's any questions in the chat. All right, so with that, I'm going to bring up our VM. I'll share my screen again. Boom, boom. All right, so now you should currently see my VM environment. Again, when you download the course materials in a zip archive file contains the VM. If you encounter any technical difficulties, let us know in the chat, and we'll do our best to assist you. So when you boot up the VM, you're going to have the username user, and the password is also user. Let's keep it simple. And I'm going to bring up a terminal, blow up the text so you can see it. And when you look at the primary level directory, there's a workshop folder. So we're going to cd into workshop. And there's two folders here, decision trees and k-means. For our demonstration and lab, we're going to use Jupyter Notebook. It's a great tool that is often used for machine learning. It's a great way to organize, visualize, and manipulate your code for machine learning. So we're going to go ahead and run Jupyter Notebook. All right, and that will, there we go. That will automatically bring up your browser, and we're now in Jupyter Notebook. We're going to go into the k-means directory, and we're going to see k-means in action. So let's go ahead. Actually, I feel like I'm getting ahead of myself because I am. Yes, because you're probably thinking, what's k-means, right? I'm so excited to be doing this. All right, so let's talk about unsupervised machine learning, right? So you have the primer to what machine learning is. Let's look at the k-means clustering algorithm. So with k-means, what this algorithm is essentially doing is that it splits the data into k groups that are closest to k centroids. I'm going to illustrate this on the next slide, so don't be too afraid of like what exactly is a centroid, right? But you have k groups, and each group is going to have a centroid, a center point for that group. And it's essentially clustering the data based on the position of each data point. So here's how this algorithm works. It's going to randomly pick k centroids, k center points. It's going to assign each data point to the centroid that it's closest to. It's going to then recompute the centroids based on the average position of each centroid point. And it's going to iterate this process until the points stop changing assignment of their centroids, right? So based on this clustering technique, you can then predict the cluster for new points and assign it to its closest centroid. So let's look at this in action, because I'm sure that was a mouthful. It definitely was for me. So here's a visual demonstration of k-means, right? So in this example here, k in this case is 3, right? We're going to pick 3 randomly generated points within our data graph, right? And so we can see here that we can create 3 clusters based on these centroids. And what it's going to do is essentially associate each point based on the nearest centroid or mean, right? So given its distance, which centroid is it the most close to, right? So this one is going to be considered a part of the red cluster. These are considered a part of the green and for blue. And then once it does this initial clustering, the centroid of each of those k cluster is going to be recalculated, and it's going to create essentially the new mean position for that cluster, right? So given these 2 data points, it's going to recalculate what it'll deem the new center and move it from here to here. Given all these green data points, it's going to recalculate its centroid. You can see that it moves to here and so on. And so now when it recomputes that new centroid, it's going to repeat steps 2 and 3 to essentially converge to the final set of clusters. So we can see here before these two green points, right, were closest to the centroid. But once they were recalculated, these 2 points are now closest to this red centroid. So now it's going to be recategorized as a part of this new cluster, right? So it does this rinse and repeat until it converges, with every point being assigned to its most closest centroids, right? So this is the final 3 clusters that were created. So why would we want to use k-means clustering, right? You're going to get meaningful intuition of the structure of the data that you're dealing with, right? It's very useful for finding groups that haven't been explicitly labeled in your data. It can help confirm business assumptions about what types of groups exist. And it can also help identify like unknown groups or relationships in very complex data sets. It only utilizes a low amount of memory. It's good implementation, so performance usually isn't an issue, and it doesn't require categorical variables, meaning categories of, hey, malware, benign, etc. You can use numerical data and you're fine. Disadvantages is that given the random choice of your initial centroids, this can definitely yield different results, right? So it's very sensitive to its initialization, as well as different K values will produce different clusters. So instead of having 3, what would it look like if we had set K initially to the value 4, right? What would those 4, how would those data points be arranged or clustered into 4 groups? And so after it performs this clustering, you're like, okay, I have 3 clusters. What exactly does this mean? What is it telling me? Well, that's on you to assign meaning to the resulting clusters, right? So that responsibility is the burden of the end user to interpret what those clusters represent. And it is affected by the scale of each feature. You want to make sure that before applying k-means, you are using a scaled data set, because unscaled data can skew your results. And we'll actually experience that or have an opportunity to observe that in our lab exercise. So yeah, actually, here's an example. So feature scaling. What this means is that features must be scaled to the same range of values. In sklearn, there's a very useful function you can call called standard scaler to do that for you. So here on the left-hand side, we have unscaled data. We have 3 categories that we can apply, but we have an x-axis ranging from -400 to +800, -20 to 60. It's kind of hard to really associate our data points with such a varying scale. Whereas if we standardize or perform feature scaling, we can now better identify the relationships of our data points. So now you can see here, we have 3 nicely well-defined clusters. And then, of course, once you've scaled your data, that's what you're going to apply k-means against. So to evaluate the k-means model, there's 2 ways of doing this. There's the elbow method and the silhouette coefficient. We should be okay with time, so I'll cover both. So with the elbow method, essentially, this helps you determine what a good K number of clusters would be, right? So for k-means clustering, what is the optimal number of clusters that you should use? This is based on the sum of squared distance, known as SEE, or SSE, between data points and their assigned cluster centroids. What this essentially means is you're expecting a prediction of where things should lie on a graph, right? And if your prediction is off from that line, you want to know what that deviation is. And so essentially that's what the sum of squared distance is. It's just looking at the deviations of these distances, calculate them in a way that will allow us to then determine what the number of optimal clusters would be. And we call it the cluster method because you can see that we have a nice elbow here, right? So this elbow usually represents the optimal number of clusters to use. So in this case, for this particular data set, 2 would be the optimal number of clusters to use. There's also the silhouette coefficient. Silhouette analysis determines the degree of separation between clusters, and these values can range from -1 to 1. So if your silhouette coefficient or silhouette score is 0, that means that the sample is very close to the neighboring cluster. If it's 1, then the sample is far away from the neighboring cluster, which is really good, right? You want to minimize the closeness of your clusters. If it's -1, ruh-roh, right? So that's an issue. That means that your sample is assigned to the wrong cluster. You want to go back and either reassess your data set in your model. So long story short, the silhouette coefficient, you want this to be as large as possible and close to 1, which is indicative that you have well-defined clusters. So here's an example. Here we have 2 clusters, and when we look at the silhouette score for each of our clusters, on average, they're coming in at about, we'll say 0.75. The thickness of the cluster labels here help to reflect the magnitude or size of your cluster. You don't want them to be too big, as you see here. You want the thickness between each silhouette cluster to be like well balanced. If we look at k = 3, right? So we can see that our silhouette score starts to decrease, right? Now we went from like 0.75 to about 0.45, 0.5. And you can see that the thickness or distribution of our clusters have also changed. K = 4 is even worse, right? We've dropped down to 0.3. And so in this example, turns out that yes, k = 2 is probably the best given the highest silhouette score, 0.75. And so you can use that to determine, hey, yep, your model is clustering your data appropriately. All right, so we're at 11:47. We're going to dive into a demo of k-means. Once we go through that demo, we'll take a quick break. I know we're approaching 11. Actually, you know what? No, we're good. Let's take a break here because I know that was a lot. So let's take a break here. We'll resume at the top of the hour. We'll go over this demo and overview of the lab as well. And feel free, get another cup of coffee, take a bio break. I'll be here if you have any questions in the meantime. But again, we'll take a break here and resume at the top of the hour. All right, it's time. It's 12 o'clock. Hopefully everyone was able to get their next cup of coffee, bio break, stretch the legs, refresh the mind. So we are about to dive right back in. So I do see that we have a question from Jamie. Is it useful to know how the scaling process to make the data more uniform is functioning, the algorithm math behind that? So when you're first starting out, like you don't have to get caught up in the math or how things are working under the hood, right? But to a certain extent, yes, it is important to eventually understand how these scaling functions are manipulating your data, right? So there's different scaling functions that take different mathematical approaches to scale your data sets, right? So for example, there's min-max scaler, which allows you to scale your data between a minimum and maximum range, let's say between 0 and 1. There's standard scaler that will scale your data based on mean, variance, and standard deviation. And there's several other approaches as well, right? So my recommendation is to experiment. That's the great thing about machine learning, is to experiment, tweak, test, see what results you get when you apply different algorithms, different types of scaling functions. Sometimes it turns out you don't need to scale your data, right? So sometimes I'll compare my scale data to unscaled data, see what results I get. So when you're first starting out, it's useful to know that what approaches exist. And then once you understand the concepts and outcomes of those approaches, dive deeper into their mechanics and how they work under the hood. All right. Yes, and thank you, Cherry. Just as a quick reminder, if you have any questions, it's best to use the Q&A feature on Zoom. Just press the Q&A button next to the raised hand feature. All right. With that, let's go into our lab. I'll make sure I answered that live. Excellent. Done. Sweet. So with this, we're going to go over to our virtual machine. When you've downloaded the course materials, the password is user. Log in, open up the terminal. We'll increase the text here. So in your parent directory, you're going to cd into workshop. There's going to be 2 directories, one for decision trees and k-means. We're going to utilize Jupyter Notebook for our machine learning activities, if I can spell it correctly. This will automatically open up your browser. Again, this is a common tool that's used throughout the machine learning process. We're going to go into the k-means folder. And in here, we have a demo that I'll walk you through. There'll be a corresponding lab exercise for you to apply what you've learned, what you observed, and get that hands-on experience. And I've also provided the solution file, so you can go through it on your own. You can even bring it up side by side and step through it. But again, if you want to take your first best attempt at it, if you're spending more than 20 minutes, definitely check out the solutions file for a hint, right? There's also a binaries directory. This will contain our binary data sets that we'll be analyzing in this example. So let's open up demo. If you're new to k-means, essentially you have different cells that represent your code. You can essentially hit Control-Enter to execute that block of code. You can hit run. There's also additional features of like running all cells, running all above, below, etc. Okay. So, and if you want to insert another cell block just to help organize your code, you can just go to insert cell above or below. You should be good to go. So in this demonstration, we're going to use k-means clustering to analyze, visualize, and predict the data points within our data set. These are the core libraries that are often used in machine learning. We're going to import pandas for data manipulation, NumPy for scientific computations, matplotlib for data visualization. Specifically, pyplot is often used for displaying your data, and as well as sklearn. This is essentially the most commonly used machine learning library in Python. And within this package, we're going to use the cluster module and specifically k-means. This line here just represents that we're executing our code in Jupyter Notebook. So this will allow us to visualize our data within Jupyter Notebook. So, right, the first step, besides importing your data or importing your libraries, you want to in this example, we're going to generate our data, right? We don't have any data to use, so we're just going to create it ourselves. We're going to generate 100 random data points, which will be stored as a two-dimensional matrix. And you can think of each column representing the y and x coordinates of each data point. And each data point will essentially represent each row of our matrix. So it's common nomenclature to use to describe our matrix as X. This is often terminology used in algebraic modeling. So we're going to create a matrix that consists of 100 rows and 2 columns that will contain random values. And specifically, they're going to contain negative values, negative random values. We're also going to create a second matrix. It'll be of the size 50 rows with 2 columns, and it'll contain essentially 50 random even numbers, but we'll add 1 to make it odd. So essentially, we have 2 matrices, one of negative even values and the other of positive odd values. And now we're going to merge these two together, right? So of our X matrix, we want to modify row 50 through 100 across all columns. And we're essentially going to reassign it the values that exist in this matrix. And then we're going to plot our XY coordinates using what's known as the scatter function within PyPlot. You have to provide the first argument are your X values. So from our X matrix, we're going to point it to all rows of column 0. And then we need to provide our Y value data. So from our matrix, across all rows, we're going to use the values in column 1. So, right, so this represents our XY data. We're going to use a size of 50, and we want our data points to be blue because it's my favorite color, in case you didn't know. And then we're going to show our graph, right? So when we do that, we have this nice graph of what looks like to be essentially what appears to be 2 well-defined clusters. And using the random function, it's going to use evenly distributed values. So we don't necessarily have to scale our data. So that's why our X and Y axes are the same. All right, so we've generated our data. Now we're going to analyze it. We're going to create our k-means model and apply it to our data set. And given our initial visualization, we're going to first use 2 clusters for our k-means model. So we're going to use the k-means function and set the number of clusters to 2. Then we're going to use the fit function to essentially train our k-mean models on our data set, right? That's what the fit function does. And this allows us to essentially create our model based on our data set. And this just outputs that you've created a k-means object with these particular parameters. So now we're going to find the centroids, right? We're going to determine the center of each cluster and display that in our graph. So the k-means library has a very convenient attribute called clusters _centers _. This will return an array of the XY coordinates of your clusters, right? So here in this example, we have 2, 2, and then essentially -1, -1. So let's plot this, right? Again, we'll use the scatter function of our data. This is just copied from above, right? So this is our blue data points. But we also want to overlay our centroids. So from our center matrix, we want to grab the X coordinate of cluster 0, right? So for row 0, column 0, we're going to grab that X value. And then for its corresponding Y value, again, of row 0, column 1, which is this here. We're going to use a size of 200, so it's a bit more pronounced, and we'll color it red. I see what happened here. Okay, well, I'll fix that. So, and we'll use a marker S, which represents a square, right? Similarly, we want to plot the next centroid, right? So row 1, column 0 represents the X coordinate of our second cluster. And then this is the corresponding Y value. We'll mark it as color cyan. And then we will show our graph. And here we go, right? So we have our data points. We see that our centroids are plotted as expected, right? With 2, 2, and then -1, -1. So this helps to verify that our k-means model is headed in the right direction. So now we're going to test our k-means algorithm, right? We're going to see how the data points are categorized across the clusters, and then use this to predict how new data points will be assigned. So there's a convenient attribute that you can use called labels, right? And this will show you for each data point in your data set, how was it labeled or clustered, right? So we can see that half of the data points belong to cluster 1, and the others belong to cluster 0. So I noticed that when I reran this, it switched. So I just want to double check the red and cyan, but you essentially get the point here, right? And so let's see, cool. All right, so given our k-means model, let's predict the cluster of, actually, no, I was right, yeah, because cluster 0 is red. Okay, we're still good. All right. So yes, so we can see half of these belong to cluster 1, which is cyan, and then half of these belong to cluster 0, which is the red one. All right, we're good. So let's test our model. So if I give it a new point, right? Let's say -1.5, -1.5. We're going to take this list and we're going to reshape it as you can think of it as a matrix of one row with 2 columns. And then we're going to call the predict function to see which cluster would this new data point get assigned to. And we can see here that it outputs 1, right? Because you would expect -1.5, -1.5 does fall within cluster 1. What if I use a positive value, right? So instead of -1.5, I use positive 1.5. I reshape it into the right format. I call predict, and it predicts that, yes, that new data point would belong to cluster 0. So far, so good, right? Our output is aligning with what we're seeing. So now we're going to evaluate the k-means algorithm using the elbow method to determine the optimal number of clusters for a data set. And I've mentioned that in order to do this, we calculate the sum of squared errors. Luckily, you don't have to do the math. sklearn will do the math for you, which is really nice. You can just focus on coding and solving the problem at hand. So we're going to create a list called SSE. We're going to test a variety of different k values within this range. And then for each k cluster, right, within our range, we're going to create a new k-means model, setting our number of clusters to that particular k value. We're going to fit or train our model based on our data set. And then for our model, we're going to use the inertia underscore attribute. This contains the SSE value for that cluster, right? That's all you have to call. You don't have to do all the math of like sum of x minus y squared. Like, no, we don't have time for that. We just want to solve the problem. So we're going to append that SSE value to our list, and then we're going to plot it, right? So we're going to plot K versus our SSE values as a line graph with blue circles. So we'll plot K as our x-axis, SSE as our y-axis. It's going to be blue with circle markers, and we want a line graph. We'll make our graph fancy by labeling the axes and giving it a title. We can also set the figure size so that it can be shown easily on your screen. And then we will show your graph. And so we got this nice pretty graph here. It's very pretty with our elbow. And we can see here that the optimal number of clusters is 2, right? So that's in 15 minutes, essentially covered how we can apply the k-means algorithm in Python, right? You walked into this knowing nothing about k-means, knowing nothing of how to implement it in Python, and we covered it in 15 minutes, right? And so what's great about Jupyter Notebook is that you can get real-time feedback, right? So what if instead of 2 clusters, I changed it to 3 or I changed it to 4? What do my results look like, right? So I always highly encourage to experiment, tweak, test. Don't be afraid to change something because you can always change it back. But the more you explore your data, the greater insights you're going to get, the greater understanding that you're going to gain in the process, right? So you're going to have a lab exercise. I'm going to go back to here. So let's open up this lab exercise. And you're going to apply the k-means algorithm to a set of binaries using their imports and exports as the features for your machine learning model. And for this exercise, we also introduce you to a tool called Leaf. It's a cross-platform library that allows you to parse, modify, and abstract different types of binary formats. And so, for example, when you import Leaf, let's say we want to load and parse the ls binary. So here it just provides you with examples of how you can extract its imported functions, exported functions. You can even extract its strings. They even give you a nice convenient function for that, as well as getting a list of functions, extracting a list of functions from that binary. So when I run this, I see that ls has 110 imports, 6 exports, 353 strings, and 296 functions, right? Knew nothing about it. Now I know even more in a split of a second. You're then going to import the necessary libraries for this exercise, specifically argparse to create your argument parser, the OS library for file system analysis and processing. We'll use Leaf, as well as the core libraries that we just demonstrated. You're going to import the k-means algorithm. And in this lab, you will need to scale your data. So from the pre-processing library, we're going to import standard scaler. So I'm just going to do a quick overview of what this lab contains and what the objective is. And then if there's time towards the end, you can do it towards the end of the workshop, or if you want to do this on your own time. It's a great way to spend your weekend. So if you have nothing to do, you can work on the lab. And again, you have the corresponding solution file. So you're going to set up your argument parser. It's going to take 2 arguments, your path to your binaries, as well as the K for the number of clusters. So you can add your code here. You're then actually going to collect your own data. So you're going to create 4 functions. The first is to determine if the file is an ELF file. You're going to create a function that returns the number of binary imports, a function to return the number of binary exports, as well as a more comprehensive function called get metrics, where essentially this is going to take a file path as input. You're going to iterate over the files in that path. You're going to use these 3 functions to determine, is that particular file an ELF binary? If so, I'm going to extract its binaries, imports, and exports. I'm going to store that information in a dictionary for each binary. I'm then going to store that dictionary into a list, and then I'm going to return the overall list of dictionaries, which will essentially serve as your data set given all the files that you've analyzed. We're going to, so essentially we've created our data set, right? Now we're going to apply k-means and plot the data. You're going to, for this step, you're going to create a data frame from the list of dictionaries. So for example, you can say my data frame equals from the pandas library called data frame. And I'm going to pass in my data set, right? So that's a hint on how to create a data frame. And again, the data frame is just a matrix to format your data into a structure that can then be further processed. You're going to scale your data using standard scaler. You're going to create a scatter plot of the data where the imports are plotted along the x-axis and the exports along the y-axis. You're going to apply the k-means algorithm to your data frame. You determine the centroids and then plot the k-means clustered data with the centroids shown, right? Most of this we just walked through, right? So with the demo and the solution file, I'm very confident that you'll be able to complete this. So after we have applied the k-means model, we're going to evaluate our model using the elbow method. And then we're going to put it all together, right? So we're going to combine the functions that we created above to collect, analyze, and visualize your binary data for this particular k-means lab exercise. So you'll uncomment this line below when you're ready. This will serve as the file path to your binaries. Remember, that's where it's pointing to this directory here. If you want to test other binaries, feel free to pass in the appropriate path. You'll, as the second argument, indicate the number of clusters that you want to use. And then you should be good to go to call the remaining functions that you create. Okay. So that's the k-means demo, as well as an overview of the lab that you have. We're approaching almost 12:30. So with that, we're going to switch over to the supervised machine learning section and give you a look behind the scenes of what's involved there, and would similarly do a demo and lab exercise. All right. Cool. So we just covered k-means clustering. We're going to quickly go through evaluating ML systems, right? This is going to be very useful when analyzing or assessing supervised machine learning models, right? We saw how we use the elbow method to evaluate the optimal number of clusters. So now we're going to look into that even more. So here are the key metrics that are often used to assess the performance of machine learning models. One is a confusion matrix. No, it's not to confuse you, but it can seem confusing at first, but don't worry, we're going to break it down. Also looking at what is the accuracy and precision, as well as recall of your model, F measure, ROC curve, and AUC curve. We're going to, again, decipher what all these mean and how they're calculated. And again, you don't necessarily need to always do the math. You can call certain functions that will do it for you to get you the results that you're looking for. So what is a confusion matrix, right? So it's a performance measurement for machine learning classification problems. This is essentially what a confusion matrix will look like. It'll show how many elements from a class are correctly or incorrectly classified. It's extremely useful for measuring accuracy, precision, recall, and all the other metrics that we talked about. So how do you interpret this, right? So say that you were expecting a value of 1 and you predicted a value of 1. That will be considered a true positive, right? So this cell will show the number of true positives from its analysis. But if you were expecting a 1 and predicted a 0, that's considered a false negative or a type 2 error. If you were expecting a 0 and predicted a 1, that's considered a false positive. Whereas if you were expecting a 0 and predicted a 0, that's considered a true negative. So how exactly do we leverage this information to calculate our metrics? So for accuracy, this is a fraction of true positive and negative examples across the entire data set. So you're going to add A and D together and then divide it by the sum of your entire data set. Whereas precision is the fraction of true positive examples among the examples that the model classified as positive. So to break that down, essentially we're taking our true positives and dividing that by the sum of A plus C, right? So you're just looking at A divided by this entire column. Whereas with recall, it's the fraction of examples classified as positive among the total number of positive examples, right? So you're taking A and dividing it by the sum of A plus B, or the row. With F measure, this allows you to calculate a single score based on precision and recall, right? So you're going to follow these steps to calculate precision and recall, multiply it together, and then double it, and then divide it by the sum of your precision and recall. This essentially allows you to create a superset metric based on two metrics to get an overall picture rather than just looking at these two precision and recall individually. You have the ROC curve, right? And no, we're not talking about Dwayne Johnson. We're talking about the receiver operating characteristic. This will compare the true positive rate to the false positive rate. So when you graph this, you get this nice curve here. And again, don't worry, you don't have to do all this math. You can just use sklearn to calculate the ROC for you, and you can assess it, determine if it's good or not. For area under the curve, or AUC, right, this describes how well the model can distinguish between classes, meaning zeros and ones. So since your AUC value will range between 0 and 1, if it's 0, it means that you're 100% wrong. So sorry to say that, but you got to go back, look at your model, reassess your data, and definitely make the necessary improvements. But if your AUC means 1, you're awesome. Your model is 100% correct. And so essentially, the higher your AUC value, the more accurate your model will be able to make its predictions. So again, you don't have to calculate this yourself. Just use sklearn to do it for you, and you can keep it moving. So we talked about these different metrics that we can utilize to evaluate our machine learning model. But there's also, you can also do this visually with regards to underfitting and overfitting. So underfitting is where your model performs poorly on the training data. It hasn't learned enough from its training data, maybe because you don't have enough of it, which results in low generalization and unreliable predictions. And essentially, your model is unable to capture the appropriate relationship between your input and output data. Whereas with overfitting, it's quite the opposite. Whereas your model performs well on the training data, but not on your test or evaluation data. Essentially, your model has learned too much from your training data, which also results in low generalization and unreliable predictions. So essentially, what your model is doing is it's memorizing seen data, and it's unable to handle new unseen data well, right? The analogy I make is that imagine you're studying, you're cramming for an exam or a certification, and you're just like memorizing all the sample exam questions. And then you get to the exam, you see a question that you've never seen before, and you just like freak out. It's like, I don't know what to do with this. I don't know how to interpret, analyze. It just fails, right? So that's equivalent to like overfitting. So what this looks like is, let's say you've plotted these data points, and let's say your model doesn't have enough information, and it's like, hey, I really can't tell what the relationship is between my input output data. I'm just going to say it's a linear relationship and just like draw a line. Overfitting is where it's just too precise. It's trying to map each and every data point. And essentially, I consider this like the drunken walk, where it's trying to hit every data point, and it's not really flexible. Whereas really, you're trying to find the best fit. You want an ideal balance where you have a good representation of the relationship between your input and output data, right? So this line here would be considered a best fit. Really just creating this arc between among the data points, right? So if you get a new data point, it'd be much easier to potentially predict where that would fall on this curve compared to this drunken walk or this, incorrect linear relationship. So that's several ways in which we can evaluate our ML models using these metrics, along with looking at whether or not our model is underfitting, overfitting, or establishing the best fit. So why did we cover all of this, right? I'm going to speed through just ahead because we're a little past 12:30. You'll see this come into play as we dive into supervised machine learning. But of course, if you do have any questions, feel free to throw them in the Q&A section. I'll make sure to address them before the end of the workshop. All right, quick sip. All right, so supervised machine learning. We are going to learn about decision trees, right? And what exactly is a decision tree? It's an algorithm that automatically generates a series of questions through a training process to decide and predict observation categories. So essentially, your questions are going to be based on the features of your input data. And it's represented as a flowchart-like tree structure, which we'll see on the next slide. But how exactly does it work? It's going to ask a starting question that best partitions the data, reducing its uncertainty as it proceeds, right? So for example, let's say you're just analyzing cats and dogs, right? There's very distinct features that you can first ask, hey, is this a cat or dog, and trying to classify an animal, right? And then it's going to ask continuous questions to increase its certainty about its prediction. You can think of this as like the game 20 questions. And it's going to stop asking questions once it has reached a certainty threshold. It's like, okay, you know what? I've gained enough information where I feel pretty confident about the predictions that the model will make. So here's an example, right? Let's say we're analyzing a binary and we're trying to determine whether or not it's malicious or benign, right? So the first question that you might ask is, given the number of suspicious calls in this binary, does it make up less than or equal to 40% of the calls? If it's true, it'll take this branch. If it's false, it'll take this branch, right? So let's say we take the true path. Then I'm going to ask another question. It's like, okay, for this binary, is the amount of data compressed less than or equal to 37%? If it's true, take this path. If it's false, it takes this path. And when it reaches this node, it can say, hey, based on how these questions were answered, there's a 38% probability that this binary is malware, right? And it's going to continue this process until it's very certain about its predictions. So let's say we took this path instead. False, I'll ask the question, for this binary, is the amount of compressed data less than or equal to 38%? If it's true, then it's like, okay, I am very confident with 94% probability this binary is malware, and it can stop its analysis, right? So you can see here, very easy to understand, interpret, explain, and essentially helps, it mirrors like how we as humans make decisions, right? So with that, reasons to use decision trees, it can predict the target's class or value based on simple decision rules that are inferred from your training data. It's very easy to explain this particular machine learning model to other people. Several benefits, easy to implement, visualize, interpret, as we just saw in that example. It can help explain the decision-making process of your machine learning model. It can handle both numerical and categorical data with very little data preparation. So you can apply this to a variety of problems. And you can also set the maximum tree depth to control the tree size and reduce overfitting, right? Because you don't want to ask too many questions and get too precise that can, one, eat up a lot of resources and can result in overfitting, because you want a general solution to solve as many to handle as many input samples as possible. But there are some downsides, right? So it's not as accurate compared to other supervised machine learning models. Small variations in your data can result in completely different decision trees, right? So you have to be mindful of that. If you have unbalanced data sets, this can result in biased decision trees. Remember, I talked about bias in the first half of this workshop. Your machine learning model is as intelligent as the data that you give it, right? So you want to make sure that you're using balanced data sets to the best of your abilities. And your resulting decision tree may not be the most optimal decision tree, right? So when you create one, always recommend of trying to tweak the parameters to generate different decision trees so that you can determine which one may be the most optimal or whether or not that particular decision tree is good enough. So to evaluate the decision tree model, right, you can utilize the confusion matrix and calculate accuracy, precision, and recall. Let's go ahead and dive into our demo. Kind of speeding ahead here because we're at 12:40. So I'm going to go ahead and close our K-means lab just to save on resources. We'll go into the decision trees folder. We have our demo, lab exercise, and lab solution. And we also have two data sets that are provided for our demonstration and exercise. All right, so we're going to analyze, visualize, and predict our data points of our data set using decision tree for supervised learning. Again, we're going to use our core set of libraries. What's different in this demonstration is that we're going to utilize the tree package within sklearn, specifically the decision tree classifier, and we're going to use export graphviz in order to export the visualization of our decision tree. We're also going to use train test split from the model selection package in order to split our data set into a training set and a test set for our analysis. We're also going to import metrics so that we can easily determine accuracy, precision, recall, etc. And we should be good to go for this demonstration. All right, so rather than generating arbitrary data like we did in the last lab, we're actually going to utilize a publicly available malware data set. You can get this off of kaggle.com. If you're not familiar with Kaggle, which I'll just type in here in the chat, it's a fantastic website that includes data sets. It's a great community for those involved in data science and machine learning. You can check out different notebooks, and they have different challenges as well. So definitely check out kaggle.com, and we'll be specifically using one of their malware data sets. So to load this data set, I do see the question that came through. I'll definitely capture that a little bit towards the end here. So we're going to use pandas to read in our CSV. This will automatically load it as a data frame, right? So to check out the dimensions of our data frame, we're going to use the shape attribute. We see that we have 373 rows or 373 Windows malware samples that were provided in this data set. Again, just to clarify, there's no live malware in this VM. The features were already extracted and then loaded into a CSV. So that's what we're actually analyzing, right? So it's already pre-processed for us or prepared for us. So 373 rows and then 532 columns. So let's go ahead and look at the top 10 samples of our data set. We see that in column 0, we have this label heading. This is classifying whether or not that file is non-malicious or malicious. And then we have 531 arbitrary features that if it contains a value 1, that feature exists in that sample, or 0 if it did not exist, right? So when we're using supervised learning, it's always great to, convert your categorical variables into numerical variables, right? So we're going to convert non-malicious to 0 to represent benign, and then malicious will be equivalent to a value of 1. So we're just going to update our data set. So for the label column, we're going to replace with the following. Malicious will get set to the value 1, and a non-malicious entry will get set to the value 0. So now let's just look at the last 5 rows of our data set to see if that took effect appropriately. And we do see that here, that in our label column, we now see 1 instead of malicious. Okay, so we've loaded our data. We've done some pre-processing on it. Now we're going to perform feature selection, right? So we're going to identify the features that we want to focus, that we want our model to analyze and focus on. So we're going to grab our header row, right? And we're just going to convert that to a list. So for our column headers, we're going to convert that to a list. We're going to indicate that of our header row, column 1 to the N represent our feature columns, and that header 0, essentially column 0, is our target, right? Again, that's our class detailing the classification of that sample. Hey, Solomon, if you can throw your question into the Q&A instead of the group chat, that'd be great. I'll just repeat it here. Is there a way to know what each feature was in this data set? What is F1, F2? Or is there an index that corresponds to each feature? Yeah, so on the Kaggle website, they provide essentially a README or description of what each of these features mean. For this workshop and this walkthrough, I wouldn't get caught up in that, but I would indicate that, hey, these are binary features that they're looking at. It could be whether a certain string existed in that binary, if it had a certain suspicious or malicious call, any attributes within that file. If it existed, it'll mark it as a 1 or not. So we identified our feature columns in our target or class column. So now we're going to essentially create subsets of our matrix here. Cool, thanks, man. From our data set, we're going to essentially capture all of our feature values, right? So from F1 all the way down to the last value of our last column, that table will represent our data set known as big X. And then our target values will be assigned to Y, right? So from our data set, let's go ahead and slice our data and just have column 0 with its respective values. As part of our data preprocessing stage, we want to ensure that our data doesn't contain any unexpected values, such as like not a number, or if there's missing blank information. So we can use this code here to check whether or not a not a number value exists within our data set. This will return a list of like true, false, etc. Of each of these data points. Is it not a number or is it a number? And then we can use the any function to assess, given this array, were any of these values true. Given that it outputs false, that means that our data set does not contain not a numbers. It does not contain any missing or blank values. Therefore, we're good to go. If this returned true, then there's additional steps that we would have to take. So just for completeness and your awareness, using that same list, you can use where to identify the I and J coordinates within your matrix of where that not a number entry existed. For that not a number entry, you can replace it with 0 using this nan to num function. It'll iterate over your entire data set and replace each not a number entry with 0. But if you want to replace it with a different value, then within pandas, you can apply fill NA. Let's say you want to replace it with a 1 instead of 0 across our entire data set, and you'll be good to go. But since our data is awesome and you're awesome, we're good to go to proceed, right? So we've loaded our data, we've done our data preprocessing, we performed feature extraction. Now let's go ahead and split our data into training and test sets, right? This is an effective approach in order to train our model, test its effectiveness, and then evaluate its performance. So using the train test split function, we're going to pass in our data set. We're also going to pass in our target, our class values. We're going to set our test size to 30, which means that 30% of our data will be set aside for testing and 70% will be used for training. My recommendation is that you don't go below 20% for your test data because that can lead to some inaccuracies with your model, and it could result in potentially some overfitting. And then random state is here for completeness. You can set this to any value. I set it to 1. You can set it to 42. That's the answer to life. But essentially, this will return 4 variables indicating the train and test sets with respective to your data set and your target classifications. All right, so now our data is ready, and we are ready to create and apply our decision tree model. So we're going to call the decision tree classifier, and we're going to now train our model based on our training set data, as well as the training set data associated with the target classification, right? Malicious, not malicious, et cetera. So essentially, we're training it across all of our training set data. Now we're ready to test our model. We're going to predict the classifications of our data set values, right? So for the data that we set aside for testing, we're going to use the predict function and predict the data in our test data set. And we can print these predictions, right? You can say, hey, for this particular sample, it's a 0, so it's likely benign. But for a lot of these samples, they're probably malicious based on its analysis and therefore predictions. So let's see how accurate this model is, right? So you can easily call the accuracy score function within the metrics library, passing in the value that you were expecting against the value that you predicted, right? And with very few lines of Python code, we developed a decision tree machine learning model with 99% accuracy. That is crazy. That is awesome. And this is why I love machine learning. So given the model that we just created, if I give it a new malware sample, its prediction is going to be 99% accurate into saying, yes, this is malicious or not. So we can generate our confusion matrix to further analyze our metrics. Metrics. So we're going to call the confusion matrix function again against what we were expecting and what we predicted. We can see that we had 16 and 95 correct classifications. 16, this would be we were expecting benign and we predicted it as benign. We were expecting this to be malicious and was predicted as malicious, but we did have one misclassification. So if we really wanted to bump this up to 100%, it was so sensitive that it needed to be 100%, so that this resulted in 0 misclassifications. We go back to our data model and our data to see what we can tweak. To get additional metrics to look at, such as precision recall and F1 score, we can call the classification report against what we were expecting and what we predicted. And we can see, for the most part, we had results that are above 90%, which is really, really good. So overall, our model is performing very effectively. And then lastly, we're going to visualize our model using export graph viz. We're going to create a dot file, and here we'll pass in our classifier, which is our model. We'll pass in the names of our features, as well as our output file, which is classifier.dot, and then we'll convert it to a PNG file. So for this run, I currently have that here. So if I open this up very quickly, minimize this. CD workshops. I see that we have about 5 minutes, so I'm going to continue as quickly as I can. So I'm going to use EOG to look at classifier.png. Blow this up, zoom in. Okay, so essentially this is the decision tree that is driving the decision making of our model, right? Essentially, it's asking as its first question, for feature F19, did it have a value less than or equal to 0.5? The Gini score helps to represent how evenly distributed your score is. The closer it is to 0.5, the more evenly distributed. If it's closer to 0, that means that the data leans more towards a particular category or class. For this question, there's 261 nodes or samples that were at this node. 55 of them appear to be benign, 206 were malicious. And then at pretty much continued its question and answer process. We can see that at the next level, the Gini score dropped down to 0.02. There were only 209 samples that took this path, 3 of them likely benign, 206 likely malicious. So you can see here how we're leaning more towards the malicious classification with the significantly lower Gini score. If we had answered false, that meant 52 samples answered false, Gini score of 0, because all of them would then be considered as benign, right? So that's a way to easily generate, visualize, analyze your decision tree model, understand the decision-making process. And from this alone, it was able to accurately predict a binary as malicious with 99% accuracy. All right, so we are at 12:56. I'm going to quickly just go through what your lab exercise will be, and then we'll stay on. I'll answer some questions, and I know that Cherry wants to provide some additional information as well. So very similarly, you're going to use a different data set of window malware samples that you're going to analyze. We already have the libraries imported for you, and we're going to import the malware data.csv. That's what exists here. You're going to perform feature selection. You're going to perform your data pre-processing, make sure it's good to go. You're going to split it into training and test sets. You're going to create your decision tree model, test it, evaluate it, generate your metrics to assess it, and then you're going to finally visualize your decision tree. Again, you have the solution file to make sure you're headed in the right direction, and you have both of these lab exercises to work on over the weekend. So just to quickly wrap up here. All right, in 2 hours, you got an introduction to machine learning. We touched upon unsupervised machine learning, specifically k-means clustering. We explored supervised machine learning algorithms, specifically decision trees, and you have a great number of metrics that you can use to evaluate machine learning performance. Again, if you're looking for a security research internship, full-time job, or new position, email me at this address here, as well as if you want to be notified of future offensive cybersecurity trainings. I offer them throughout the year, so love to engage with you again. And again, follow me on Twitter at that handle, as well as Ring Zero to stay up to date on our upcoming events. So with that, boom, we did it. We've done it. We done did it. All right. So we're going to take some questions here. I'm going to take a quick sip. And as we're going through the questions, if you enjoyed this workshop, let us know in the chat. Ring Zero has done an amazing job to put this together with the support of Cherry volunteering as well. So show some love and praise in the chat. All right. So questions. This is from Noah. Which of these techniques have you used for vulnerability discovery? So far, decision tree makes sense, but I imagine something crafty can be done with deep neural nets. Yes, so for vulnerability discovery, and this is something that we do go into in my class that's being offered in February as we analyze several different types of machine learning algorithms, is that what's tricky with with vulnerability discovery, right, is that a vulnerability can exist or present itself in different ways, depending upon, like within a binary, depending upon the language it was written in, the compiler that was used, the optimizations that were used, if there was any obfuscation or encryption involved, etc. So you have to have a great understanding of how the vulnerabilities exist within that binary, so that as you're applying an algorithm, right, you want to be able to recognize what a vulnerable, say, function looks like compared to a function that's secure, right? So how can you go about making the determination to say, yep, function secure, function not secure. So in that case, for the most part, I would say that supervised machine learning algorithms is a great start. With neural networks or deep learning, essentially that machine learning model can figure that out for you with very little, I would say, domain expertise, depending upon how your data has been crafted. And so my recommendation would be to first start with different types of supervised machine learning algorithms. Once you get the hang of it, then explore, okay, how can I solve this with deep learning or neural nets, right? Because with neural networks, you can solve problems that both unsupervised and supervised learning algorithms are used for, right? It's sort of like a catch-all. So, and isn't as, I would say, limited or constrained compared to unsupervised versus supervised. So that would be my recommendation. You really have to understand how the vulnerabilities exist, or like what those vulnerable patterns are, so that your machine learning model can detect it accordingly and come to the right decision that, yes, this is vulnerable or not. All right. Solomon asks, well, first, outstanding workshop. Thank you so much. Appreciate it. Thank you for attending. Book recommendations. Do you have recommendations on which books give a decent start on this type of analysis, as well as the libraries you went over? Great question. Shout out to our public libraries, by the way. They need some love right now. So you can't go wrong with any of the machine learning library books that are available via O'Reilly, as well as No Starch Press. There's a lot of great blogs online as well, such as like Towards Data Science, big fan of them. And so, yeah, I mean, I would essentially just Google around machine learning books, machine learning blogs, and, you know, in our course, in the class that I teach in February, we provide a variety of different resources to further explore, but that's a good starting point. Towards Data Science, and then O'Reilly and No Starch Press. All right, so we have one question. How do you deal with packers and malware while classifying malicious or benign? Great question. So essentially, you can use that as a feature, right? So looking at how much of your data is packed or not packed, right? Similar to how much of our data is encrypted or not encrypted. And it's when you compare it to benign files, right? It's very easy to start detecting, I would say, these patterns of deviation or maliciousness, whether that data is packed, compressed, encrypted, obfuscated, etc. So depending upon your data set, you can, again, utilize that as key features to hone in on in your model in order to help inform your machine learning model to come to the appropriate conclusion that, yep, based on packedness of this malware, it can likely lean towards this file being predicted as malicious or not. All right. So yes, if you want to get in touch with me, in the slides that are provided via the link to download the course materials, you can get my email address, which again, here on this slide. If you want to follow up with me after this workshop, or if you have additional questions about the classes that we offer in February for Ring Zero, which I go into much greater depth, definitely feel free to email me at this address here.